For a short introduction, I would like to hand over to the first speaker here. It's Tony Adamson from NXP. Tony is Strategic Marketing Director for NXP's vehicle networking transceiver portfolio and has worked with NXP on in-vehicle networking for the last 9 years. He has 15 years of experience working in product and strategic marketing, having previously also worked for Philips, Advanced Development in the UK, TomTom Automotive in Amsterdam. He's today responsible for driving strategy and innovation for NXP within CAN-FD, CAN-XL, and 10BASE-T1S. So, Tony.
Yeah, thanks very much for the introduction. Well, let me share my screen. And like everyone should be able to see that. Okay, so thank you very much, and welcome everyone to this session on day 3 of the iCC. My presentation this afternoon will be about CAN signal improvement and how that opens up the possibility to run CAN-FD at 5 megabits per second. Due to the setup today, I am the sole presenter, but otherwise I would be accompanied by my colleagues Axel Engelhardt and Edmund Sang, who are also strong contributors both to this work and to the paper that's included in the proceedings as well. So what I will try to do here is basically give a bit of a summary of that paper and just to sort of look on a high level about this topic. The main 3 points I want to bring across this morning is if you look at real practical networks, so with multiple nodes in a bus, CAN-FD will typically be limited pretty much to 2 megabits per second, where maybe the next step up would be 5 megabit that I consider. With CAN signal improvement, which is a new technology that's been developed and now standardized within the CAA community, we can enable CAN-FD networks to now really operate at 5 megabits, and again in real practical networks. And that's coming from 2 factors that the CAN signal or CAN-SiC, CAN signal improvement transceivers are bringing. The first one of that is an improved transceiver symmetry, and the second is the signal ringing reduction, and we'll look at both of those in this presentation. And then as I go through, I will talk a bit about some case studies that we've done together with some external parties, looking at network simulation, just to make it a bit more tangible for you in this presentation. In the paper itself, we go into a little bit more detail on some of the guidance and recommendations for how you would actually develop a 5 megabit network. I think there's probably not scope to do that within this talk, so I will reference a couple of points, but I strongly encourage to read the rest of the paper to get all the details. So let's first, by way of recap, start on why 2 megabit is the limit for typical CAN-FD networks. So we know very well from very simple CAN principles, you have a dominant level, you have a recessive level. Dominant is below the 0.9, recessive is below the 0.5, and at some point I'm making a sample point to determine what the voltage will be, the differential voltage. And so very simply, a network topology must guarantee that the differential signal is stable at the sample point in order to ensure reliable communication, and specifically under all worst case conditions. Now, when we speak about all worst case conditions, we speak mostly about timing asymmetries. Those have the possibility to move the sample point around in the recessive phase, in fact, in all phases. But most important, we care about this worst case, which would be 5 dominant bits and then immediately generating some signal ringing going into the first recessive bit. So we need to make sure really that the signal is stable at this sample point. Now, although this paper is talking about 5 megabit in general, I'm using a 2 megabit example here just to make things a bit easier. So here I'm also using a 70% nominal sample point. And then if I bring in all the different asymmetries, they can actually move this sample point most significantly earlier in the bit time. And in the paper, we go through all the different reasons about what that would be, but very simply to summarize, it's the oscillator, it's the transceiver asymmetry, the PCB tolerance, and also if you're just missing one time quanta in your receiver, then that could potentially move the sample point much earlier in the bit. Now, what I want to focus on is really the transceiver asymmetry, because that is by far the biggest component. And you can see both the symmetry of the sending and receiving transceiver can add up to 90 seconds. And if you look in total, rather than now a sample point of 350 nanoseconds, I can have it in the earliest case, 209 nanoseconds as my earliest possible sample point. That's significant reduction in the amount of time I have to support signal ringing. So from that, we can define what we call the earliest possible sample point and the latest possible sample point. And as I say, from a simulation perspective, we normally would care about the earliest one because there may be some signal distortion as the recessive bit will start. But we can also say, well, anything before the earliest possible sample point, we don't actually care really what happens to the signal there. All kinds of ringing and signal distortion effects can take place. So this is what we call the allowable ringing time. We know there, by definition, that it's ahead of the earliest possible sample point, that we would never sample there and never consider the signal there in our CAN-FD controller. So to then extend that out across this whole worst case, or this whole bit pattern, sorry. In fact, every dominant bit will also have an asymmetry area around this nominal sample point. And so together with the part on the recessive and the dominant, we can basically mark these as a mask or sort of areas to avoid. And likewise, then the green area that you see is then the safe operating area for the CAN signals. And then through simulation, we can basically use these masks to judge, is the signal going to be valid, yes or no? To make a bit of a simplification of that, here I've just redrawn this in a small animation. And I'm now looking at the recessive bit together with the last dominant bit that I would have before that. And again, just representing all of this, again, another visualization, exactly as we saw on the previous slide. Now, why is this limited basically to 2 megabits per second? Well, what happens if we increase the bit rate up to 5 megabits per second is you see that the gap between the latest dominant sample point from the previous bit and the earliest recessive sample point becomes very, very close. And actually, I have very limited room to get any signal through using standard transceivers. So that means I have to have a very well terminated network in order to make sure that that signal will be stable and will fit through that safe operating area in order to guarantee communication. That fact is basically limiting us to say with standard CAN transceivers that you buy today, using the values in the ISO specification for the asymmetry, I'm pretty much limited to 2 megabit for these larger networks where I would have signal ringing. And if I want to go to 5 megabit, I'm effectively limited pretty much to a point-to-point connection. Certainly not something that I could use to span over the vehicle and have different style connections on. And so it leads us into basically looking at how CAN signal improvement can actually help us and move towards 5 megabits per second. And let's continue with looking at the transceiver asymmetry. So CAN signal improvement is now defined within the CIA 601-4 document that was finalized last year, I believe, or 2020, yes, correct. And that is also including in its definition much tighter transceiver symmetry parameters than the previous ISO specification had. So to look a little bit more in depth, this is, as you see on the screen, is the values from the current ISO specification. And this is written in a form that's linked to a 5 megabit bit time. So the nominal bit time there would be 200 nanoseconds. And then you can see we have a variation possible on the transmitted bit width coming from TXT going onto the bus, then being received at the receiver, and then ultimately how big that bit is allowed to be at the RxD pin on the receiving controller. Now, as an aside, there's been also some definitions, and I will use that in this presentation as well. So just to clarify, transceivers which are fulfilling these are now defined by the CAA to be called a CAN-FD transceiver. So they have to be compliant to this 5 megabit bit timing specification. Now, what I would like to do is actually just rephrase these calculations and rephrase these numbers to make them now as bit time variations, so that actually we take away the fact this is associated with a 5 megabit value, and we just make it versus a nominal bit time. And so here we can basically take the 155 and 210 nanoseconds here and rewrite this value to be minus 45 and plus 10. We take exactly the second value, minus 45 and plus 15 here. And then for this last value, from 120 to 220, we can now write this as a relative number, so minus 80 and plus 20. This is much more intuitive in a way because it's not linking to any particular bit time that would be otherwise used in the application. And even the fact that this is referring to 5 megabit is even quite confusing, because many car makers are saying you need to be compliant to the 5 megabit bit timing specification in order to be used for a 2 megabit network. And that can be a little bit counterintuitive. Why I re-express this is because how it is expressed now in the CIA specification is to actually tighten this, but still using that same deviation number. So we don't now write it with respect to a nominal bit time. We just say that the deviation is now tightened instead of minus 45 and 10 to minus 10 plus 10, from minus 45 to 15 now to minus 20 plus 15. The total is now minus 30 to plus 20, as opposed to the minus 80 plus 20. Now, if you're wondering why these numbers do not add up together, but they do here, this is basically saying that the total budget is here minus 80 nanoseconds. Any one of these two components can actually be up to minus 45, but the total budget you actually have available is minus 80. So what does that mean? Why is that actually relevant? Well, let's go back to this visualization. Here again, we have now our CAN-FD transceiver with its asymmetries here. So here's my nominal bit time, and I'm now looking at my earliest recessive sample point. And these are my two asymmetry values for my transceiver. Now, if I put in the new CIA numbers, these become significantly smaller. In fact, I'm saving about 60 nanoseconds of symmetry here. So that gives me a lot more time for ringing. Certainly at 2 megabit. So that means I can even tolerate more ringing within a network just by the fact that I'm having better symmetry numbers before I'm even doing anything about the signal improvement. But what really becomes important is when I go to 5 megabits per second. 60 nanoseconds is 30% of the nominal bit time that I'm now improving. And that means that I can run a CAN-FD network with now some signal ringing in the early phase, and still run this now at 5 megabit per second with CAN-SIC transceivers. And that's the really big enabler that these transceivers are providing in order to open up the possibility for CAN-FD communication at 5 megabits. So that really means I can now have multi-stub topologies running and still being able to guarantee the communication. Now, as an aside, you can actually even go, you see, much faster than this with CAN-SIC transceivers. Now, we also mention here in the paper, you actually see that at this point now, the latest dominant sample point will start to become the limiting factor if we're still sticking to sample points of around sort of 70%. So actually, if you want to even go beyond 8 megabits per second, beyond 5 megabit, maybe to 8 megabits per second, then we're also advising that you're moving the sample point a little bit earlier, even very close to 50%. And that actually will give you the most amount of margin when going to super high bit rates. Now, what you need to make sure is that that device that you're going to be using will guarantee these bit timing specifications at these high bit rates. The CIA 601-4 requires that these numbers are compliant up to only 5 megabits per second. But our first product generation we have launched, which is the 146X, we're actually guaranteeing this up to 8 megabits per second. So that means that then you still have this guarantee of the performance even at these higher data rates. Okay, so that's a bit about then the timing symmetry part. But let's have a look at also the signal ringing reduction, which is another key point of CAN signal improvement, in fact, why it's called CAN signal improvement. And for this, I'd like to actually walk you through a case study that we did, where we took a CAN-FD network, which is today running with CAN-FD transceivers. This is actually a very large topology, and it's a very, very linear topology as well, you can see. So it's basically a daisy chain with just a few stubs coming off on the main chain. I have two terminated nodes here, B and W, and then basically this long line of nodes going all the way through. The actual construction of this was taking the two cables and basically putting that into a connector slot to create the daisy chain connection, which would be possible for this network, but for example, in power chain networks or anything which would be sensitive to humidity, that would not be allowed. So we'll be also introducing additional connectors. Now, what we did was we took this and we actually then mapped it to a multi-stub topology, and we developed this basically out of our own sort of imagination, but used very much on the theory that we'd seen from other classical CAN topologies. So it's kind of based upon what we could see, and then we mapped this to a real vehicle, as you can see here. This is a very complex topology, so lots of star points, lots of branches coming off. We still have the termination resistors in the same place, but also crucially, this is actually a little bit more, from a functional safety perspective, this is actually a little bit more robust than a otherwise daisy chain topology. The reason would be, for example, if I had a cable break on, if I take, for example, ECU L, and then I would have a corrosion on the connector here, I would have the potential basically to lose two of those pins and potentially split that network by basically creating a cable break. Now, in this case, L is just at the end of a small stub by itself. So should there be any corrosion on that connector, only that local module is affected, and the rest of the network can continue completely by itself. The other key benefit of this is, in our calculation we made, we can save more than 1/3 of the cable length by moving towards this multi-stub topology. So there is also huge cost saving from going towards these style of networks. What we would do is basically take this network and put this into a big simulation tool. And how we do that is we first of all build the topology in the simulator. And then we would build a matrix, and that you can see here, of all the sending nodes at A to X. And then we make a matrix then with sending to all the other nodes, including itself. And then we create this very, very big matrix of communication. And then we execute a network simulation. And what we'll do is we'll take that criteria that I introduced earlier in the presentation and basically use that as a mask to assess, is the network communication reliable, yes or no? And then we can simply grade that as a pass, a marginal pass, or as a fail. And that gives us a very beautiful table like this, using standard CAN-FT transceivers. And you can see here, there are some clear failures, which is why this customer was not using such an extensive multi-stub topology at 2 megabits per second. It's simply not possible because there's too much ringing. And here we can actually see an example of one of the worst performing nodes. And you can see on the overlay, these red areas that I've described, these are again the areas to avoid that we're using directly in our network simulation to judge whether this is working, yes or no. This may look a little bit different to what I've introduced. So this big red box here is the 5 dominant bits, then you have the 1 recessive here. And let me just briefly explain what these other two are. We also include 1 dominant and 1 recessive as kind of the opposite extreme of how we would do the network simulation. And there's also a good reason for this. We've noticed, if looking at the left-hand side, this is again just using the standard 5 dominant, 1 recessive. We can actually have still a passing result appearing. But in this network, we had also a lot of ringing on the dominant edge, and that was then carried through into the next recessive signal, which is only picked up when doing 1 dominant and 1 recessive. So by using complex stimuli, we're actually able to have much more coverage about what really will be the effects in the network simulation. Now, then what we did is repeated that network simulation for using CAN-SIC transceivers, and basically then here you see the result. And even that very complex topology is now running very reliably, and everything here is green. And here you can see the change in results. So you see actually here we have still some distortion on the recessive signal, and that's actually almost mirroring the distortion you would have on the dominant side as well. So this is just pure topology effect. So it's still very, very heavy in terms of signal ringing, but we are able to bring that under control. Also, you see here represented the area to avoid in the recessive signal is actually narrower, and so we're already calculating in the tighter symmetry values that the CAN-SIC transceivers offer. So this network is now reliably working, so that's great. A little bit of recommendation also is something that we do in simulation is to use actually a typical simulation model. So when doing network simulation, you may have the option to do either a typical or a worst case simulation model. Our recommendation for anyone who wants to do their own simulation work or wants to develop a CAN-FT topology, maybe now at 5 megabits per second, is actually to use a typical simulation, which will be a much closer approximation for a bench, then in combination with this worst case timing criteria that I identified at the beginning of the presentation. The reason we recommend that is a number of reasons. Basically, the worst case simulation model, in combination with the worst case timing asymmetry, is just too unrealistic. And that's because the simulation model is driving all datasheet parameters to their very limits, even if actually some of those combinations are completely unrealistic. Secondly, we also see that the transceiver's transmitter, or the output driver, has actually much better stability over temperature than maybe sometimes the datasheet limits are predicting. And even if this is having an impact, it's typically due to temperature. It's having the effect it's having is then changing its timing performance, which we already then will account for in the worst case timing symmetry parameters. So in fact, it's pretty safe to use the typical simulation model. Now, why is that good? Well, number one, okay, it's always nice to increase the achievable operating space of the network and support bigger networks. But actually, we are doing this in a fair way by eliminating only the over unrealistic corner cases. But the real benefit is that if you're doing a network simulation, or even you're not at that stage yet, you can very easily cross-check this with a bench test. So you can just run this now in a room temperature in a lab and do a very simple bench test, and then use the criteria and put that as a mask on your scope, and then you can easily see, hey, is this topology going to work reliably or not? And so you can debug your topology in a much easier way without having to do each time a full network simulation. So typically what we recommend is you build up your topology, you come to something which you think is looking good, and then do a network simulation afterwards to reduce the simulation burden that otherwise you might have. That also increases the cycle time in order to get towards a good working topology. Okay, now I talked about 5 megabits, and actually I've told you thus far about a case study for 2 megabits. So I wanted to do that because I think it's a very illustrative example, just showing on really what CAN signal improvement transceivers can do. But let me now come back to also 5 megabits as well. So here's also a CAN-FD network that's actually working today at 2 megabits per second using CAN-FD transceivers. And so here you can see also on a network simulation, everything is looking green. But if I now accelerate that up to 5 megabit, exactly for the reason we were explaining before, just due to the fact that even though there is limited signal ringing, any signal ringing basically cannot really be tolerated in the network because the margin in order to get that signal through is just so limited. You see here that it's just every node is having at least one failure. Now again, upgrading this towards something like a CAN signal improvement is quickly bringing that signal under control. And again, here you see that's due to both the increased symmetry, giving us more margin, but also here due to the signal ringing reduction. And here you can see a comparison on the left-hand side with the CAN-FD transceiver, and on the right-hand side, the performance with the CAN-SIC transceiver. And then basically one other example, and I use that also just to give a nice ringing example, and this is also referenced within our paper. This is a star topology we made with a star point termination of 60 ohms, and then 2 nice 4-meter unterminated stubs. And you can see here, even running at 2 megabit, just to make it a little bit clearer and show more of the signal with CAN-FD transceivers, you can see a huge amount of ringing here. And at 5 megabit, this is just completely not working at all. And yet again, due to the improved performance of the CAN-SIC transceivers, both in terms of the ringing reduction, and also you see here that first spike is getting close, but we're still able to basically manage that due to the improved symmetry. Then this network is working very well at 5 megabits per second. So lots of results. Just to really simplify it, though, I think we've kind of seen this as being a general guideline, and I'm not going to swear to this in blood, but just in a general guideline, what we've typically seen is networks operating reliably today at 500 kilobit with CAN-FD transceivers will just work reliably at 2 megabits per second with CAN-SIC transceivers. Due to the fact that we are able to reduce the ringing, we have that better symmetry performance. So that's giving us the possibility to still tolerate a lot of signal ringing and give us a good reliable performance. Likewise, networks typically operating at 2 megabits per second with standard transceivers will today just more or less work at 5 megabits with CAN-SIC transceivers. Again, it's not a hard and fast guarantee that I can give you here, but at least that's in our experience what we've seen, and even I would say we can often do even a little bit more. So that's generally a safe guideline. I know one customer actually asked us to prove this, and we were actually proven right in their exploration. So I was very happy about that. So that's basically concluded the majority. So just a couple of slides to round off on this presentation. So just to sort of summarize a bit, the real potential that CAN signal improvement is offering. So again, it's offering the capability to run really now large star-based CAN-FD networks that are giving you basically much more freedom in how you're designing your network, giving you much more possibilities to reduce the cabling costs, really design actually the cables you would like to have. And secondly, it's allowing you to really run proper networks at 5 megabits per second. And we now start to really get traction and a lot of customer interest in these kind of requests. You're getting a lot of payback in terms of saving cost and weight. And I think one of the real advantages of CAN signal improvement is it's also available just as a straight changer for CAN-FD transceiver. So it's a very easy upgrade for your network. You don't need to change anything on your microcontroller. I mean, if you want to go to 5 megabit, of course, you need to do some reconfiguration of your software, but nothing in your hardware application really needs to change. So if I compare that also, and I'll go ahead, as we're talking also today about going from CAN to CAN-FD to CAN-XL, we're kind of opening up a bit this step in between CAN-FD and CAN-XL, where I have a much lower threshold of effort in order to gain this improvement in my bit rate. I don't need to change my microcontroller. All of the typical micros would anyway be available. And yet I'm really able to access this next step in bit rate and performance, giving me a lot more capability in how I run my CAN-FD network. So we really think this is giving a really nice and powerful option for network managers to think about and access ahead of them the next generation of CAN-XL networks. And so with that, I'd like to close my presentation. Thank you very much for your attention.